In this tutorial, we are going to talk about the simple pendulum and simple harmonic motion. So let's start. Let's say we have the pivot and we have the equilibrium position in the middle with our bob like this, and this is the bob mass at the equilibrium position or at a fixed point, that dotted circle, and from here we have the bob that we are about to swing, and in the string we have a force tangent T, and the string is of length L. So we also have the weight of the bob going downwards. You know, the weight always acts downwards, and our angle theta here, it means we can resolve this. So going down here, we have mg cos theta, and this way we have mg sine theta. So another scenario, we can also have the pendulum on this side. Just same concept, and we are saying the amplitude is the maximum displacement from the equilibrium position. So this is the equilibrium position, so the amplitude is this displacement, and we denote it with x naught or capital letter A. So this is all on simple harmonic motion. Let's look at some of the equations that we are required to know under the simple pendulum. So you can be asked to calculate the period. So the period is denoted by T is equals to 2 pi square root the length over g, where g is the acceleration due to gravity. As we already know that g is 9.81 meters per square second. And we can also be asked to calculate the frequency. The frequency is the number of complete oscillations per unit time. So the units can be revolutions per second or hertz. So this is 1 over t, but t, we already know how to calculate t. So this can be f is equals to 1 over 2 pi square root of length over g. So we can write this as the frequency is equals to 1 over 2 pi g over L. That's how we calculate the frequency, where L is the length of that pendulum. So what is simple harmonic motion? What we are saying is a periodic oscillation in which the acceleration is directly proportional to the displacement from the equilibrium position. And the acceleration is always directed towards that equilibrium position. So this can be referred to as a fixed point or equilibrium position. So that's, those are some of the formulas we should know under simple pendulum. We can also be asked to calculate the angular frequency, W, which is given as this. Or you can write theta is equals to WT. So since W is equals to theta over T, and we know that 1 over T is equals to F, it means we can write W as 2 pi multiplied by F. So that's all we are required to know on simple pendulum. So let's move on and talk about simple harmonic motion. So we have already defined simple harmonic motion, where we said it's a periodic oscillation in which the acceleration is directly proportional to the displacement, and we should remove the proportional sign and introduce an equal sign, and our constant is W squared x, and we put a negative, which indicates that the acceleration is always directed towards that fixed point or the equilibrium position. So let's go ahead and derive this equation. So we have an equation for the displacement to time graph, which is x is equal to x naught, which is the amplitude, sine theta, but theta is Wt, so x is equals to x naught sine Wt. So it means we have a sine graph linking the displacement to the time. We can draw that graph to clearly visualize what we are talking about. So we have something like this, where we have the time and we have the displacement, and this is the maximum amplitude that we are talking about, which is the maximum displacement from the equilibrium position. And this straight line here, that's the equilibrium position. So let's go ahead and derive the equation. So let's look back at some of the techniques on differentiation. So let's say y is sine theta, it means dy dy the theta is equals to cos theta, and if y is equal to cos theta, if we differentiate that with respect to theta, we get negative sine theta. So let's apply that here. Let's first differentiate x, which is our displacement, with respect to time. to find the velocity. So velocity is dx dt. So if we differentiate sine wt, we get w cos wt. So we get w cos wt, but we already have x naught, which is our amplitude. So let's go ahead and find the acceleration. So the acceleration is defined as the rate of change of velocity. So we are differentiating our velocity with respect to time. So we already have x naught and w here. So let's differentiate cos wt. If we differentiate cos wt, we are going to get negative w sine wt, like this. So let's remove those square brackets. We are going to get acceleration is equals to negative x naught w by w, get w squared sine wt. But what is x naught sine wt? This is equals to x, and this is the x naught sine wt. So finally we are getting there. It means we have our negative x naught w squared sine wt equal negative w squared x naught sine wt, that's x. So finally acceleration is equal to negative w squared x, which we've reached our final. We have derived the simple harmonic equation, and this equation describes simple harmonic motion. You can see that the acceleration is directly proportional to displacement, which implies that as acceleration increases, what happens to x? Now, as x increases, as the displacement increases, acceleration also increases, and as the displacement decreases, acceleration also decreases, which implies that these two, they are directly proportional to each other. And w squared, that's a constant. The negative sign indicates that the acceleration and the displacement are always directed or measured from a fixed point or from the equilibrium position. And w squared, that's our angular frequency. So that's all we need to know on the simple pendulum and simple harmonic motion. From here you can solve any problems. So in my next video, I'm going to be solving problems for you so that you can master the concepts and understand simple harmonic motion further. So get ready for the next video. Don't forget to subscribe on my channel. Thank you.